Well, good afternoon. Collin Homer with USGS. Wanted to acknowledge Matt Coho with BLM, my co-author on this presentation. What I thought I'd do is just give you a really brief background on the remote sensing side. I've been in the business for a long time. I can't help preaching about it, so you just have to forgive me. I'll move into some background of how these products were developed, a little bit of what the products are and what we're doing with what you could potentially do with them, and then close with a little bit of the future. A reminder that our brains are very visually oriented. If you've ever looked at photographs or satellite imagery, you can look at it and you can see a lot of information. You can make sense of it. You can get excited about it. So from a monitoring point of view, you can even see change across time. And you look at that and go, that's really cool. That's exactly what I need. The challenge is coming up with an algorithm to capture that. And that's what we've been struggling with for a lot of years is how do we capture that kind of change. So going into a better way to characterize shrub and grasslands, we had some guiding principles on the GS side we worked with for a lot of years. And the first thing is you need to recognize arid and semi-arid shrub and grasslands are very difficult remote sensing environments. They take a lot of stuff you have to throw at them to be successful. We're interested in large ecosystem science and management questions. They're very complex and difficult. So we need consistent data sets over large geographies. We wanted to make sure the method we developed is quantifiable, repeatable. You know, if you can't measure it, you can't monitor it. That sort of thing. Working at multiple spatial scales, and if you're going to monitor, it's got to be cheap and easy, or you can't sustain it. So those are sort of the set of criteria that we went in a few years ago to develop our method. One other remote sensing perspective is if you've been exposed or been in the business very long, there's kind of two fundamental ways to categorize that information you're seeing. One in kind of classes or categories, and the other is called fractional veg, which is a more subtle continuous field way to characterize it. I'll talk more about that in a minute. But I just wanted to point out there's advantages and disadvantages for both approaches. We work with classes. You have a local scale classification, very targeted application. That's usually the better way to go. Very hard to repeat. You have a more generic, wider area sort of strategy you need to repeat over and over, like a monitoring example. The continuous field or the fractional veg is a better way to go. And that's the direction that we've gone here. Okay, so a little bit of background. Most of you, if you work in the arena, you use some kind of Dobbenmeyer frame. I want you to picture this is a 1 meter Dobbenmeyer frame plopped on the ground. You got about 25% sagebrush in that. You got bare ground, you got grass, you got litter. All we're doing on the remote sensing side is using pixels with Dobbenmeyer frames. So we can send thousands, we send crews out and get thousands of these 1 meter frames that eventually get walked up to a satellite prediction. So just like there's, let's say, 25% shrub in this 1 meter frame, in this Landsat, the 30 meter cells, 30 by 30 meters, think of them as a frame, and we're making the same proportional estimate of shrub or sagebrush in these pixels. So that's all there is to it. We scale up from 1 meter frames on the ground, and just like you can measure different things here, we measure those different things in the satellite. So, nice thing about it, you can measure across scales. Some oil platforms in Wyoming here, you can see a 2.4 meter frame or satellite pixel scale. This is a bare ground estimate. Do that at 30 meter. This is our wall-to-wall satellite here. We can even do it on a coarser scale. This was also looking at some of the different costs involved, but that's kind of how to think about this. Anything you need a per pixel estimate to is a way that this product is designed to be used. Now, just wanted to point out back to my first point that semi-arid shrublands are a difficult remote sensing environment. We have to throw a lot of data and effort to be successful. We use a regression tree, which allows us to data mine sometimes 50 to 70 different independent layers, different satellite dates, ancillary data. We throw slope and aspect, a whole bunch of things that are data mined into these predictions that I'm going to share with you. The first place we really scaled this up, steered it to, was in the state of Wyoming. And again, start out with these 1-meter frames strategically placed on the landscape. They actually classify a high-resolution satellite scene. These are these red chips here across the bigger wide area satellite scene, a coarser scale. Here's the whole state, and you can see where these high-resolution satellite collects are strategically placed to develop a model for the entire state. So that's how we scale this stuff up from the ground. Well, about this time, we enter AIM as a collaborator, and we're working with AIM now to develop these products across the western U.S. And so this was the first geography where we did additional scaling up to say, okay, yes, we want to do something at the ecosystem, ecoregion scale, and be consistent so we can answer some of these really tough questions about monitoring, things that we're grappling with. How do we operationalize that a little bit further? So this is the first geography that we worked on to do that. With a couple key developments, we're now doing shrub, grass, bare ground, wall to wall. The Wyoming example I showed you was just in the sagebrush step. Now we're doing it from the Mojave Desert to the alpine zone. So we're covering everything. And to do that, we need to use climate zones. We've come up with a very intensive mosaic approach. We've got Landsat 8 now, which helps us got a few more bands. And we've got Worldview 2, and I'm just throwing some of these names out in case some of you have been exposed to this. With our high-resolution satellite, we're using Worldview 2 now. It's really well-performing, gives us really good predictions at this high-resolution scale, sagebrush and the bare ground. And then those are eventually walked up to the Landsat scale, which is that same geography. And the product suite that, and I'm just basically showing you that so you can see there's no edge lines in it. Okay, that's no message there. A little hard to read, but this is the product suite we're developing across the western U.S. now. So there's, this is the satellite scene itself. Per pixel, remember the satellite frame on the landscape now is a suite of products that nest. They're designed to be used in comparison and in contrast in complementary fashion one with another. Shrub, we make a sage cover estimate, a big sage cover estimate. We actually do shrub and sage height estimates. This is not LiDAR, it's optical, so they're not the best estimates, but they are estimates. We make an estimate of herbaceousness, forb and grass, and annual herbaceousness. So since we do a spring, summer, fall, we catch different green ups, and we can make an annual herbaceous estimate. We can even do a cheatgrass, but that's, so kind of think of that as usually in most geographies an annual invasive estimate of bare ground and a litter cover estimate. Okay, how do we validate these? How do you know how good they are? We have 3 different ways. We do independent validation, we do a cross-validation of our model, and then we output spatially the absolute error of all of our products. So just in this case, you have a shrub prediction here. You can see the absolute error. The absolute error is in the units of the prediction in percent. So you'll know for every pixel what our model, what the model confidence was in making that estimate. For those of you that want to look at some independent validations, here's 2. We finished the Mojave. We finished that northwest zone that I was telling you. We're modeling shrubs from the Mojave Desert on the Mexican border to the alpine zones and subalpine zones of the Steam Mountains here in this set. And R squares can be higher than this, but this gives you, I'm showing you this to show the relationship that we usually see as bare ground can perform quite well. This is at the Landsat scale. We do amazingly well at litter. Herbaceousness varies in shrub. Again, it depends on the variety of the landscape. Root mean square errors, usually for a shrub, is 5 or 6, plus or minus 5 or 6%. Bare ground is plus or minus 8 or 9%. So this is where we're doing what, where, and when, how. 2002, this is this area that I've shown you here. So the date here is the nominal date for the year that product is characterized. We finished the Mojave. We're finishing now this Idaho and Great Basin piece. And these are the geographies planned for this upcoming year. We moved into the Sonoran Desert here in just a month and move into these geographies here. It's very much in the northern area, centered around where we need it for sage-grouse. So what I'd like to finish up a little bit with is paint the picture. Well, how does this work for monitoring? We've had a lot of research that's been going underway to prove out that this is a good way to look at the landscape. What we're trying to do is be as consistent we can on the landscape scale, but being as relevant as we can on the local scale. So it's not only good enough to come up with something you can kind of look at consistently at an ecoregion scale, but is it good enough you can use it to sort of apply where you're going to get to first base on the local scale? Co-authors that I've worked with, another thing to demonstrate it works really well for sage-grouse habitat. We've done it across Wyoming, the entire state, as well as the Gunnison sage-grouse. Done a grazing assessment. We can show using this approach where land health standards are going to pass or fail. I've done a lot of climate work. I'll show you just a little bit of that. Got a whole bunch of fire fuel analysis, basic monitoring, restoration monitoring, a whole lot of work in play here that will show and demonstrate even a little more how well it works. So when you think about this from a monitoring standpoint, from a very simple standpoint, there's two different years. 2006, a fire occurs between 06 and 010. This is a bare ground estimate. The more color you have here, the higher proportion of bare ground. And we can pick the fire up with a bare ground estimate. More importantly, for every 30-meter cell, we can quantify exactly what the bare ground is, okay? So that's how this stuff starts to work across time. So in terms of monitoring on the ground, we have a site in Wyoming. We field measured, satellite measured, at various scales for 8 years now. Here's a report out on the first 4 years of that. This is a increasingly wetter period of time. Again, this is 4 years. The precipitation is going up, and in a significant fashion, we can use these approaches to see this is the bare ground falling down a few percent, and the shrubs growing a few percent across these years. So on the ground, we've been able to demonstrate, and this is all written up. If you'd like to read it, this is an article coming out soon. The neat thing now, though, is we do this on Landsat. We have a 30 to 35-year archive now we can exploit for historical trajectories. And this is an example where we went back 30 years, again, very variable systems with precipitation. There's a downward trend across that with less precipitation over time. In this case, I'm showing you our sagebrush estimate. We're seeing the same sorts of things. Cell by cell, we can model this relationship and develop a slope, and using forecast precipitation into 2050, start to show you cell by cell where we think, depending on the precipitation scenario, the amount of bare ground and the amount of shrub and sagebrush and other things will be on the landscape. So in this case, where things are, the greener they are means the more bare ground, the more orange in the shrubland, it means the less shrub. So, you know, bare ground is going up, shrub is going down, if you follow these patches out to the year 2050. The kind of scary thing about this is in a Wyoming zone that's supposed to be fairly stable when you look at climate predictions. So we're now exploring this another more unstable thing. Knowing those kinds of things, though, we can then plug sage-grouse habitat into this and show you in the year 2050 under this precipitation scenario, just using climate as a disturbance. This is where we expect, in this case, nesting habitat to change. With the red, is just as you would expect to happen with climate change, your patches nibble in from the edges. And we saw about a 12% loss of nesting habitat in this example here. And we can do the same thing on this is a cheatgrass example in Nevada. We can go back and quantify the change across time. So this is how this would envision, you can imagine with an AIM kind of approach, if we can repeat these things, which is planned, we can start to define the trajectories of bare ground and herbaceousness and annual herbaceousness and shrub and all kinds of things, not only across that 30-year record, but start to say something about how that will perform in the future. So that kind of just gives you a taste of how we anticipate this is used in the monitoring framework. The other point I wanted to make in closing is this is part of the National Land Cover Database. So we envisioned the National Land Cover Database as the land cover change census of the nation. So in case you think this is what I do on the side, if you think your local backyard is changing a lot, you really got to think of the poor folks in the Southeast. That's where the land cover change is really going on if you look at this from a national point of view. But the point I want to make is this shrubgrass effort is now under the umbrella of the National Land Cover Database, which is really important when you look at how we're going to sustain this effort into time. What will the future look like? We're now funded and doing the base characterization, which I've described to you. Some geographies are being done back in time, and we plan to do eventually the wall-to-wall back-in-time products as well. Moving forward now, working with AIM, we plan to repeat this every 5 years. So this is a monitoring effort. You will have these predictions locally to be done every 5 years. So if you can think of any way you can take that whole suite of components in a way to interact and use those, you'll have a reliable, dependable, system-wide product to work with. We do anticipate some quick annual update scenarios where fire occurs, those kinds of disturbances. We can update on a more frequent cycle than 5 years. As this can work among scales, we anticipate it evolves to not only finer time scales, but it can be done space scale with sort of hotspot approach, and are looking for this to become a fundamental monitoring product that works in a lot of arenas and for a lot of agencies that need these sorts of things. With the National Land Cover Database, we've had a lot of success in just developing a repeatable product and are amazed by how much these things really get used once you establish that. That's all I have to say. I circled the website at the bottom to remind you some of the initial products will be coming out soon, and if you want to download those, that is the website where we'll eventually make some of these shrubgrass products available with that northwest piece I showed you first available hopefully in about 3 or 4 months, and then you'll start to see products flow after that. So that's all I have for you. Thank you. Do we have time for any questions? Anybody have any questions? So we are using Landsat 8 now. Landsat 8 has a couple advantages. It has a couple more bands, and it has better bit depth. So it's kind of like a high-resolution TV versus a regular resolution, a high definition. We found probably a 5 to 10% accuracy improvement from Landsat 8. The real challenge with Landsat 8, though, is when I show you the back-in-time stuff, you go 30 years back, we have to directly compare Landsat 8 to Landsat 5, which is causing a little bit of grief for us, but we worked around that. So Landsat 8 is great moving forward, not so good if you're making historical comparisons to the step cousins, Landsat 5 and 7 then. Any other questions?
Yeah, are you going to have words you can actually
Yeah, we anticipate doing some of that through this initial website that I showed you is the bulk aisle in the grocery store. I mean, we have some needs that just want it that we'll just put bulk files there. But we also at this site have an interactive tool where you can window your own size and you can interact and view that a little bit. That will take a little more time to get into that tool, but we anticipate eventually. But to start with, you'll just need to download a fairly large file and flip it out yourself, because we want to get it out the door as soon as we can. Everybody's ready for a break. Thank you.